Chapter 19. Work and energy in rigid body dynamics. In this chapter, the method of work and energy will be used to analyze the plane motion of rigid body and system of rigid body. Also, the principle of work and energy is well suited to the solution of problem involving displacement and velocity. From Newton's second law, we learn if the resultant force acting on a particle is not zero, the particle will have an acceleration proportional to the magnitude of the resultant and in direction of the resultant. Also, we learn the general plane motion. In the general plane motion, the rigid body is undergoing both translation and rotation simultaneously. When the rigid body undergoing general plane motion for translation motion, the resultant force equals to the mass of the rigid body times linear acceleration at the center of gravity. Also, in general plane motion, we have rotation. So this rotation make a moment about any arbitrary point in the rigid body. So the resultant moment about gravitation center point equal mass momentum mass moment of inertia times alpha as the angular acceleration. In this chapter, we will use work and energy in rigid body that directly related to the force, velocity, and displacement. And we are going to how we find the work and kinetic energy in the rigid body. From previous chapters, we learned work and kinetic energy are scalar quantities. Assume that the rigid body is made of a large number of particles. So we have U equals T2 minus T1. T1 and T2 is initial and final total kinetic energy of particles forming body, and the U1 to 2 is the total work of inertial, internal and external forces acting on particle of body. Look at this figure. As you can see, the internal forces between particle A and B are equals and in opposite directions. Therefore, the network of internal forces is zero. By this concept, we are going to talk about the principle of work and energy for rigid body. The principle of work and energy states that the work done by the external and internal forces and coupled as the system moves between two positions equals to the change in the kinetic energy of the system. We can find the work by this equation: force times R2 minus R1 plus moment times T2 minus T1. And kinetic energy equals 1/2 times mass times V squared plus 1/2 moment of inertia times angular velocity squared. Let's look at how we find these equations. Before that, we learned the work of force during a displacement of a point of application found by this equation: force times displacement. Look at this figure. Consider the network of two forces, F1 and negative F2, forming a couple of moments during a displacement of their point of application. So the work equals F1 times dr1 plus F1 times dr2 minus F1 times dr2. The summation of these forces we can write F times ds2. Instead of ds2, we can write R times d theta. As you can see, force times R as a displacement is M. So we have M times d theta. So the work from point 1 to 2 is combination of this equation and that equation. Now we find the work of force in the rigid body. Now we have to find the kinetic energy of rigid body in plane motion. Consider a rigid body of mass m in plane motion consists of individual particles I. The kinetic energy of the body can then be expressed as a T equals 1/2 m times mass times v squared plus 1/2 summation of mass times v squared. Instead of v squared, we can write r times angular velocity, r omega. So we write r squared times m times omega squared. This term represents the moment of inertia. And this is the omega squared. As you can see, we got this equation. The first term is represent the kinetic energy associated with the motion of the mass center G, and this term represent the kinetic energy associated with the rotation of the body about G. The same concept what we discussed about conservation of energy for particle will be used for conservation of energy for rigid body. So if all the forces that do work on a system of rigid bodies are conservative, the sum of the total kinetic energy and the potential energy is the same at any two positions. Also, when both conservative and non-conservative forces do work on a system of rigid bodies, the principle of work and energy can be expressed in terms of the potential energy V for conservative forces and the U for non-conservative forces. Let's look at one example. For the drum and flywheel, the moment of inertia is 10.5 pound feet second square. The bearing friction is equivalent to a couple of 60 pound feet. At the instant shown, the block is moving downward at 6 feet per second. Determine the velocity of block after it has moved 4 feet downward. The block is moving downward at 6 feet per second. The bearing friction against the motion. This one is moving downward, so the friction is against the motion and it's equivalent to a couple of 60 feet, pound feet. Also, we have angular velocity, but we don't know the magnitude. Consider the system of the flywheel and block. The work done by the internal forces exerted by the cable is cancelled. Now first we have to find the angular velocity, is meaning omega 1. We know that the relation the velocity of the block and the angular velocity of the drum and flywheel are related by this equation. The V1 is 6 feet per second and the R is 1.25 feet. Now we can find the omega 1. After that, we apply the principle of work and energy to develop an expression for the final velocity. For the T1, we write the equation. We know that all the parameters just we substitute here. How about the T2? We don't know the V2. We have to find it. And also we don't know the angular velocity, omega 2. But we know that the velocity and angular acceleration are related by this equation. So instead of angular velocity, we write the V2 over 1.25. This is the kinetic energy after the object fall down 4 feet. Okay, but for the work, we have to write the first. For the work, the weight of object is the only forces acting on a rigid body that do the work. For this reason, we have W, the weight of the object, we have displacement, S1 equals 0 and S2 is 4 feet. Also, we have a moment. We put the negative because as you can see, the moment is in opposite of the direction and also it's a clockwise, okay? So negative 60. How about the theta? We can find the theta by this equation. For the theta 1, the S1 is 0, so the theta 1 is 0. The T2 is this location. We have S2 is 4 feet, the R is 1.25 feet. So by this equation, we find the T2. When we substitute to this equation, we find the work. After that, we have 3 equations, T1, T2, and the U. Write the principle of work and energy. T1 plus U equals to T2. By this equation, we can find the velocity of the object. The velocity is 12.01 feet per second in downward. Thank you for watching.